All right, so the last class we began with chapter 3, which is bonding and structure, and we talked about ionic bonding, which involves the transfer of electrons between the atoms of elements. And the whole point of bonding is because the atoms of elements, when they're reacting, they want to achieve a noble gas configuration. That means they want to have a full outer shell, right? Now,
Yeah.
ionic bonding occurs between metals and non, right? And it affects their physical properties and chemical properties as well. And the example we gave was sodium chloride. So sodium has one outermost electron and chlorine has seven. So one electron is transferred to chlorine. And so the outermost shell is emptied. And so the next shell is a complete 8 electrons for sodium. So sodium's happy. Chlorine gains one electron, and so that gets a full shell. So it's happy as well. But the fact that sodium lost an electron, it gains a positive charge. And chlorine gained an electron, so it gets a negative charge. And the right, what we get are ions, and those ions are held together by an electrostatic force. So that's the attraction between the opposite charges. Right? If they're similar charges, they would repel. Right? In this case, opposite charges, so they're attracted. Right, so the diagram used is the dot and cross diagram. Now you don't need to draw the detailed structure of the atom, you can only draw the outermost shells. In this case, right, because sodium is lost electron from the outermost shell, all you write is the symbol for sodium with the plus sign for its charge, or something 1. And because chlorine has a full outer shell now, you draw that, showing the dots for the chlorine electrons and the cross for the electron cross for the sodium, and thus the negative charge. Okay. Then we talked about oxidation and reduction. So oxidation is when electrons are lost, and reduction is when electrons are gained. So you add on to that, right? What we talked about oxidation reduction in the earlier classes is that oxidation is the gain of oxygen, reduction is the loss of oxygen, right? So the term oxidation reduction is has, you know, it's used in different ways in different scenarios, right? So the gain of oxygen is oxidation, loss of oxygen is reduction, the loss of electrons is oxidation, the gain of electrons is oxidation, and right, if we get to that point, we actually come across another, right, let's say definition of scenario where the term oxidation and reduction is used. So a third, redox is when reduction and oxidation occur simultaneously, right? So that is for the both of those that we studied so far. And so talk about, right, you had sodium, elemental sodium, you have elemental chlorine, and now as sodium chloride, sodium lost an electron, so it got oxidized, chlorine gained an electron, it got reduced. And so other examples of oxidation and reduction, with iron 2 going to iron 3, that's oxidation, copper 2 going to copper 1, that is reduction. Okay. Now what we're going to talk about is ionic structure. So, right, ionic compounds form giant crystal lattices, right? Giant ionic lattices. And so, if you've seen a grain of salt, right, it's a crystal,
Yeah.
right? And if you look at it on an atomic level, it's not just one sodium and one chlorine, right? So that crystal, salt crystal, is not just one atom of sodium combined with one atom of chlorine. In the case of sodium chloride, right, because they have charges and so they're able to, like, the ionic bond is one thing, but because the charges, what they're able to do in the space around them is that they're able to sort of attract 6 chlorine atoms. Now remember, they're only bonded to one, right? But we're talking about attraction here. And similarly, each chlorine is also attracting 6 sodiums. So that's one sodium. In fact, I shouldn't draw the line like that. So how many do we have? 1, 2, 3, 4, 5. Something like that. We just turn this into a dotted line to avoid confusion. Okay. So, right, and so you can imagine how massive that structure would be, that each sodium, right, is surrounded by 6 chlorines, and each chlorine is surrounded by 6 sodiums. And obviously, for a much better illustration, I will take you to the book. Just put that on screen. Yeah. Oh, come on. Okay. All right. Can you see that?
Yes.
So that is what the structure actually looks like. And so there are millions of sodium and chloride ions in there, right? And in those millions, as you can see, if I just zoom in, right? And so you see the chlorine over here, the yellow, and it has got 1, 2, 3, 4, 5, and 6 sodiums around. Okay.
Yeah.
And similarly, you take any sodium and you can see that there are 6 chlorines around it. And so for each of those. And right, so this is the kind of structure, giant lattice that is formed for ionic compounds. Over here, right, this is another ionic compound, cesium chloride. And you can see that, right, it's kind of similar, right? So they say the cesium chloride, the green box is the going further box for the O level book. Right, that's the IGCSE, going further for that one as well. Right, and so, right, in this case, cesium is surrounded by 8 chlorines, and chlorine is surrounded by 8 cesium ions. So that's 8 and 8 in this case. The point is that these structures get massive, right? And the reason for them being so big is, right, the way the ions are arranged. Again, this is not to be confused with the bonding itself.
Okay.
Okay.
Yeah.
Then we move on to properties of ionic compounds. And so
Properties of ions in a compound.
ionic compounds.
Okay.
So we know compounds are right molecule, right, uh, have atoms of different elements coming together to form a new substance, right?
Yeah.
So if that compound was formed by ionic bonding, then what are its properties? And obviously, right, the properties of an ionic compound will be based on the fact that it is made up of ions. Okay.
Yeah.
Right. So what do we have? First of all, they are usually solids at room temperature with right high melting and boiling points. And the reason for that is, again, because of the electrostatic attraction between the ions. Okay.
Yes.
And so, right, because that's a very strong force of attraction, right, a lot of energy is required to weaken that attraction and separate the ions. So that's the first thing. Second, they're usually hard substances. Third, they dissolve in water, right? Mainly dissolve in water. There might be cases where they dissolve in something else, but they mainly dissolve in water. And the reason they do that is because water is what you call a polar solvent, right? So it has a slight charge on it. I'm not going to go into detail on that just yet, but water is a polar solvent, right? And has slight charge. And so because it has a slight charge, now why it has a slight charge, and I won't talk about it right now. But the fact that it does have a slight charge, and you know these ions are made with these ionic compounds are made up of ions which have charges. And so when the sodium chloride goes into water, right, what happens is the ions separate. Okay, and they are kept separated if I use this symbol for water. Okay, water is H2O, and so that's a hydrogen, that's a hydrogen, that's an oxygen. Okay, and so the way they're kept separated is right, the sodium and chlorine both are surrounded by water molecules. And again, what's playing a role is the fact that water has a charge. And just to make it a bit clearer, right, the oxygen has a slight negative charge. So what I've written over there, that symbol is called delta, which means slight. And the hydrogen has a slight positive charge, so delta positive. And so, right, sodium is attracted by, the water molecule surrounded oxygen going first because of the slight negative. So again, right, the difference and in the case of chlorine, right, it is surrounded by water molecules with hydrogen going first, again because of the delta positive or slight positive charge. Is this making sense?
Yes.
And so when ionic compounds are put into water, they dissolve, right? And so water is a solvent, and right, ionic compounds are the solute. Right, so the water is a solvent for
Yes.
ionic compounds. Now, building on this, ionic compounds, they conduct electricity when molten or, right, in aqueous solution. Aqueous solution basically meaning dissolved in water. Right, so dissolved in water. And why does it happen? It happens because as a solid, they do not conduct electricity. Do not conduct electricity as solids. And the reason being is because electricity is a flow of charge. And the solid state, right, the ions cannot move. We just talked about the structure, they're like giant lattice structure. They're all in place, they're hard, right? So they cannot move, they cannot flow. But when they're molten, that means they're liquid, and recalling the states of matter, right, and the kinetic particle theory and all of that. So when they're molten or when they're in solution, we just talked about what happens when they're in water, right? The ions get separated. And so when molten or in solution, right, the ions can flow. And the ions have charge. Thus, they can conduct electricity. Does that make sense?
Yes, sir.
Are you sure?
Yeah.
Okay. All right, so there'll be more about this in later chapters as well, right? So solubility will be something that will be discussed in chapter 8. Electricity and chemicals will be discussed in chapter 5. All right, so these topics will be touched upon later on as well.
Okay.
Now, that's clear. Right, the next topic in the book is the formulae for ionic substances. And this basically goes on to explain something that I've already covered earlier. We just go back to the chapter 9 that we did. Right, and that includes basically how we figure out, right, the formulae of different substances. And so aluminum chloride and iron oxide and copper oxide, these are all right, ionic. because metal and non-metal.
Yeah.
Okay,
Okay.
so you can read through the book for that, but I've actually already, the gist of what they are going over in the text is something I've already explained, and I would recommend you do that today. Right, so you just go to the book and you see the topic formulae of ionic substances. All right,
Okay.
and read through that, and if there's anything that is unclear after you've read it, you can we can address it in the next class.
Okay.
Sure. Then, all right, what they talk about is oxidation numbering. So I'll put the heading here. And I'll write refer to the source text, right? Concept covered in earlier lesson. Okay, and of course you can always uh, ask. Okay, then oxidation number. So this is where we come into what I was talking about. We'll, another way of talking about oxidation and reduction. And so oxidation number is basically, right, how many electrons, right, has the atom gained or lost. Now keep in mind, right, talking about a gain or a loss, right? And so
Yeah.
what we can have, for example, is we can have something, and I'm just talking about hypothetically over here, right? We can have something, let's call it X, and it has an, so, right, it has an oxidation state of, for example, 3 minus. Okay? And so
Yes.
at this point, you would say that it is reduced because 3 minus basically means that it gained 3 electrons, right?
Yeah.
Then it went from 3 minus to just a single negative charge. What would you say happened?
He lost all three of them.
He didn't lose 3 of them, he lost 2 of them. Well, it,
Sorry, it lost two of them.
right?
Yeah.
So what we call this is that the oxidation number increased. Is this an increase?
No,
Why not?
it decreased. It lost.
How? It was 3 negative charges. It went from 3 negative charges to a single negative charge.
Yeah. So it decreased.
It increased. The bigger the negative number, the more negative you are. Right? If for example your score is -5,
Yeah.
and then you go from -5 to -2, has your score increased or decreased?
Oh, okay. Okay. It
Right?
increased.
I mean, using math over here would be good, right? So you can make a number line. Right? You got 0, 1, 2, 3, -1, -2, -3. Right? And so the more negative you are, right, the smaller the value. So you were here, and
Yeah.
now you are here. Right? So is this an increase or a decrease?
It's increased. Okay.
Increase, yes.
Okay.
Okay.
It's like first, second, third.
Kind of. I mean, if that's what, if it helps you to understand,
Yeah. Okay.
right? So, right, the oxidation number increased. Now, another scenario, right? You've got element Y, and it had an oxidation number of 5, and right, it is oxidized because right, it lost electrons, right?
Yeah.
I mean, it is already oxidized in this particular state. X with 3 negative charges already reduced, but a reaction happened, and Y went from a +5 positive charge to a +2 positive charge. What would you call this? What happened to the oxidation number?
It increased.
Again, number line. All right, so if I extend the number line, right, 4, 5, and 6, and you were here, you went from here to this point. Is it an increase or a decrease?
Decrease.
Decrease.
Okay.
Decreased. Because even though it's positive, the positive value became smaller. So it's a decrease. If the negative value becomes smaller, that's an increase. If the negative value becomes even bigger, so if it's right, -3 goes to right, -6, that is a decrease. Right? And if Y goes to 6 plus, that is an increase. Right? So if a positive value becomes bigger in terms of being positive, that's an increase. If it becomes smaller than whatever value it was, that's a decrease. And if it goes into the negative, then obviously, right, it's obviously a decrease. If a negative value becomes less negative, that's actually an increase. Okay?
Okay. Yes.
Okay. So this is how oxidation numbers can change during reactions. There are examples of this. Now, the definition I was talking about, right? So oxidation, right? We already talked about oxidation being a gain of oxygen or loss of electron, right? Oxidation can also be, right, an increase in oxidation number.
Okay.
And reduction, right? A decrease in oxidation number. Now, if you think about it, it's not exactly, well, it's not different from, right, loss of electron and gain of electron. Why? Because what's happening over here when it's going from -3 to just a single negative charge? What's happened?
Could you repeat that?
I'm saying that this particular definition of oxidation reduction
Hmm.
is not different from what we had earlier, that oxidation is a loss of electrons and
Yeah.
reduction is a gain of electrons. It's just another way of saying
Yeah.
why is that, right? So if we take a look at this, you had this particular atom that had a -3 charge, right?
Yeah.
That means it had 3 extra electrons,
Yeah.
right? It went from -3 to just a single negative charge. So how
Yeah.
many extra electrons does it have right now?
2.
How to? It's a single negative charge. What does single negative charge mean? How many extra electrons does it have?
None.
One, right? And
Yeah.
that means going from 3 minus to just a single negative, it
Yeah.
lost electrons. Right? That's what happened over there. Make sense?
Yeah.
And then look at the Y. Okay, so whatever atom Y is, it had an oxidation state of +5. That means it had lost 5 electrons. And it went from +5 to +2. So what happened?
It lost.
If it were lost, then it would have become a greater value in the positive. Right? It would have gone from +5 to +6 maybe, or +7. Because
So it gained.
yes, again, right? The charges, remember the charges, the oxidation state. When you gain electrons, right, it becomes, if you're starting from zero, it goes to negative. If you already have a oxidation number, then it decreases, right? So what's happening over here? It gained 3 electrons.
Yeah. Okay.
Isn't that the same that we studied earlier?
Yeah.
So this is pretty much another way of saying that, oh well, right, the atom is losing electrons or the atom is gaining electrons. But this is more generalized. Why? Because sometimes the numbers stay in the negative or they stay in the positive, and so that can be confusing. So that's what I was trying to clarify right now, and I hope it like work.
Yeah.
Are you sure? You don't sound very confident.
Uh, I think I'm fine. Yeah.
Right. So you can review this. Obviously, you can read the
Yeah.
book.
Yeah.
You can revisit the recording that will be uploaded later.
Yeah.
Right. And right, if it still doesn't make sense, we can go over it again.
Okay. Uh, I'll get back with you.
Hmm?
I'll get it back with you once I review it again.
Okay. And so, right, they go on to mention, right, how in the book uh, different compounds are used, right, to oxidize or to reduce, and what happens in them. So they, right, can read through this. They give the example of potassium magnate 7. In fact, I think I will write this down for clarity of explanation. Right? So they give examples. They give the example of potassium manganate 7. Right? Remember that the oxidation number is written in Roman numerals brackets.
Okay.
Right? And this guy is, the color is pale purple. And this is added to, right, a solution of iron 2 sulfate. Right, so the oxidation state of iron is +2. It's lost 2 electrons. Sulfate. What happens? Right, the iron sulfate changes, right, from pale green, it's pale green, and the color changes to pale yellow. And what this tells us is that the iron 2 sulfate has actually become iron 3 sulfate, which means it has, right, the oxidation number has increased. Has it?
Yeah.
and so it has become oxidized. What's happening to the potassium magnet? Well, the potassium magnet, right, it goes from, right, magnet 7 to manganese 2.
Okay.
Right, and that means what? The oxidation number has decreased, hasn't it, going from 7 to 2?
Yeah.
And that means this guy has been reduced. Right, and obviously a color change occurs, right? This was pale purple and this guy is pale pink, very
Hmm.
pale pink as the color. So that is one example. Okay,
Okay.
and right, they give another example of potassium iodide, and right, it's oxidized uh, to, right, sorry, it, yeah, so potassium iodide is a common reducing agent, and right, it is oxidized, it changes color, goes from colorless to yellow brown, right?
Yeah.
So they give that example as well. So we already done one example. They give two other examples as well. They give an example of potassium iodide and iron 2, right, a solution of iron 2 compound, right, and iron 3 going to iron 2, and then they also give an example of, right, magnesium and sulfuric acid reacting. So you can read that, right, the concept is the same and they explain it in the book.
Okay.
And then they also talk about oxidizing agent and reducing agent. Remember what those are?
Yeah.
What's an oxidizing agent?
Oxidizing. It gains. It gains oxygen.
it
It gains. It gains oxygen from the other element.
it's an oxidizing agent. It oxidizes the other guy.
Yeah.
So it's not gaining oxygen. Right now, however you look at it, you look at oxidation as the loss of electrons, an increase in the oxidation number, or the gain of oxygen. Right? Oxidizing agent oxidizes, right, another substance, and is itself reduced. So whatever the case of the oxidation it may be, it gives oxygen to the other guy and loses oxygen, so it's reduced itself. It takes the electrons from the other guy, right?
Yeah.
So it's reduced itself, right, and oxidizes the other guy, or it causes the oxidation number of the other guy to increase, and its own oxidation number is decreased. That's an oxidizing agent. And on a similar note, a reducing agent,
It loses the oxygen and gives it to the other element.
well, definition, right? Not how it's working. So it reduces another substance and is itself what now? Oxidized.
Yeah.
Right? So it's reducing the other guy, so it's taking its oxygen, or it is giving the other guy electrons, or it is reducing its oxidation number. Whatever's happening, that's what a reducing agent does, right? And itself becomes oxidized.
Okay.
Okay.
Yeah.
Yeah, and that is the end of the ionic bonding part of this chapter. Right, so next up is covalent bonding, and I guess I will leave that for next class.
Yes.
Okay, but, right, the parts that I asked you to refer to in the text, please do that. So that if there's any query, any ambiguity, it can be discussed in next class, hopefully. Right?
Okay.
So please do
Yeah.
that.
Yeah.
Right, and also the examples of the oxidation reduction reactions that are given in the text. I've discussed one of them. There are two more that are given, so read those, see if they make sense too.
Okay.
Okay,
Yeah.
so we will continue with covalent bonding in the next class, inshallah.
Inshallah.